If you've studied statistics before, you've probably heard about the null hypothesis. Previously, we talked about different hypotheses for our example. H1 was the number of people with narcissistic personality is higher in applicants than the general population, and we're given the general population of 1%. So let's break this apart and see if we can construct statistical hypotheses based off of this more scientific hypothesis. We might have H1, or the alternative hypothesis, as the proportion of Big Brother applicants who scored high for narcissistic personalities is higher than members of the public. And we might have a second hypothesis, the null hypothesis, which is Big Brother contestants and members of the public will not differ in the proportions of scoring high for narcissistic personalities. Why do we have these two different hypotheses? Well, we need a null hypothesis in hypothesis testing because we make an assumption based on the null hypothesis. And then what we do is we project what the data would be like if that assumption was true. If the data disagree with that assumption, we then project that hypothesis in favor of an alternative explanation. In this case, the alternative hypothesis. So often, something that you're trying to measure or prove or understand ends up being the alternative hypothesis, because we're only ever trying to reject the null hypothesis or see if the null hypothesis is rejected. You don't really want to try to reject it. So let's go through this. The proportion of Big Brother applicants who score high for narcissistic personalities is 11.15% from our data, and the proportion of members of the public who score high for narcissistic personalities is 1%. And the probability of this happening by random sampling is very low. So we would write, we reject H0, or the null hypothesis, in favor of H1, the alternative hypothesis, and conclude that more Big Brother applicants score higher for narcissistic personalities with some level of confidence. And we haven't got a sense of error or of confidence yet, but we'll get there soon. When we think about statistical models, that's how we come up with a sense of confidence in our conclusions. But why do we model more generally? Well, we model to simplify. If we want to design a bridge, we may want to simulate it first. This is cheaper, it's faster, it's safer than building a whole bunch of bridges and have people walk across them to see if they break. But we cannot capture everything about the real world in our models. So what we do is we aim for a good fit for our purposes. So if we have a real world bridge, we might model it in a very similar manner. We might get a moderate fit. Maybe we can't quite get that good fit. We don't have the resources to do so. And we might have a poor fit that probably wouldn't serve us in the ways that we want to analyze this bridge. And we'll dive into more detail about the different ways that our models might have more fit depending on the model as we proceed in this course. But I want to leave you with one quote, one of my favorite quotes from a statistician: "All models are wrong, but some are useful," by George Box. We have to keep in mind that our models are always simplifications, they're always approximations, and we want to choose the right one based off of what we think the right fit is for our purposes. So we have to have a clear understanding of our purposes. When we think about statistical models, you might be thinking about something like a regression model or something very possibly more complex. But the mean can be used as a model. It's one of the simplest models, and so it's very useful to look at it directly as a model. So for example, let's model how many friends statistics professors have. We might ask 5 professors, and we might get our data: 1, 2, 3, 3, and 4 if we ask 5 professors. If you ask me, this sounds like it's maybe a little bit high for statistics professors, but, don't ask me. So the average statistics professor from our data set has 2.6 friends. Note that this is a hypothetical value. It would be very strange to have 60% of a friend. Maybe they're a frenemy, but a little bit more of a friend than an enemy. Maybe they're somewhere between an acquaintance and a friend. Who knows? But this summarizes our data. It's a simplification. You can say, on average, statistics professors have 2.6 friends. Is it a good fit? Well, we have to dive in a bit deeper to figure that out. Let's calculate the error by summing the deviances. So this means for each observation, we can measure the deviance, the difference from the mean. So if we plot this, we have the number of friends, and we have the average, which is 2.6. We go through each observation and look at the difference. If we sum up the deviances, we arrive at 0. Woohoo! We did it! Great! It's a perfect model. Not quite. The data still varies, and we haven't captured that in our model. So instead, we can capture variance by calculating the sum of squared errors. Sum of squared errors would be the squares of the deviances that we found last time. And we arrive at 5.2. The variance is the sums of squares divided by n minus 1. In this case, we have n equals 5, so n minus 1 is 4, so we have a variance of 1.3. This can be hard to interpret, so often what we do is we calculate the standard deviation, which is the square root of the variance. This is the square root of 1.3, which means we have a standard deviation of 1.14, which gives you a sense of how widely this distribution can vary. The standard deviation shows how well the mean represents the data. So let's look at a different data set. Here we've asked about an overall lit rating of a lecturer, and we find that with lecturer 1, we have a standard deviation of 0.55. So that means that the average rating is quite consistent. The data doesn't vary very much, and the mean is a very good model of the data, or at least a better one than this, where we have a higher standard deviation of 1.82. So here we have histograms of two different distributions with the same mean, but large and small standard deviations. So again, these two numbers really give you a sense at how the variance of the data is represented. And so it really gives us a sense of how well this model, the mean, models the data. So the mean is a simple statistical model that can be fitted to data. For example, statistics professors have 2.6 friends. And we can represent how well it models that data. So we can say statistics professor I has 2.6 plus epsilon of I friends. And this is very true in statistics generally. So the outcome, so an individual outcome or observation is the model plus some epsilon or some error. And we'll dive into this in more detail in future lessons. So the key takeaways of this lesson is that this course will require comfort with many statistics concepts. Statistical models, tests, and graphs rely heavily on an understanding of distributions, measures of central tendency and dispersion, variance, and hypothesis testing. This will help us evaluate statistical models, so make sure you're comfortable with fundamental statistical concepts and review these if you haven't seen them in a while. Thank you so much, and I'll see you next time.